The basic processes of making steel have been around for thousands of years. Today's steelmaking still abides by those methods, but it is guided by sophisticated technology and precisely refined to create steel that is stronger and lighter than ever. It takes a large team of skillful people to see steel successfully through its production journey. Each person is responsible for one small but critical part of the journey. Over the next few minutes, you'll see what's involved along the way. Steel's journey begins with raw materials, which are shipped and prepared carefully to ensure optimum quality through the entire process of making steel. Coal is one of three major primary elements used in making the iron component of steel. The material is delivered to a coal field, where scrapers move different types of coal to designated piles. These different types of coal will be blended in precise proportions in a coke oven to ensure quality for the demanding blast furnace requirements. In the coal fields, sprayers coat the piles with a mixture of oil and water to form a protective, dust-minimizing coating over the material. The coal scrapers deliver the required recipe of coal to a conveyor that transports the coal to a stock bin above the coke oven battery. This battery contains several narrow oven chambers. A Larry car on top of the battery takes coal from the stock bin and dispenses it into each oven, where it bakes for about 18 hours. During this operation, coke oven gas is generated, collected, and cleaned for use as fuel throughout other steelmaking operations. Other chemical byproducts can be sold for a variety of uses. The material that exits the coke oven is pure carbon, or coke, which serves as fuel for the blast furnace. While still red hot, coke is pushed out of the oven and is transported to be immediately quenched, or cooled, with water. The quenched coke is now screened by size and then sent on to the blast furnace by conveyor. Iron ore pellets, one of the other primary elements used in making iron, are delivered to the ore field. From here, cranes and conveyor belts move the pellets to another system of conveyors that load the iron ore, coke, and also limestone into the blast furnace. Here, the materials are heated to temperatures above 1900 degrees Fahrenheit. The coke serves as the fuel to melt the iron. The melting limestone and dolomite float to the top of the heavier molten iron, carrying impurities with it and forming a layer of slag. Once the iron reaches the desired consistency, a hydraulic drill pierces through the furnace's tap hole to release the pure molten iron into runners that direct it into insulated rail cars, or torpedo cars. Liquid iron contains high levels of sulfur, which can affect the quality of steel. So before moving on to the steelmaking facility, the torpedo car passes through a desulfurization plant to bring down the iron's sulfur levels. Now, the molten iron is ready to move on to the steelmaking facility. To begin this process, the torpedo car is rotated to pour the molten iron into a ladle that will transport the iron to the basic oxygen furnace. In basic oxygen steelmaking, two main materials are required: liquid iron and scrap steel. Scrap is delivered to a handling yard near the steelmaking facility so that it can be sorted. And just like coal, scrap comes in many different varieties. A magnetic scrap crane selects the correct mixture of different grades of scrap and places it in a transfer car, which moves into the steelmaking facility. A crane then lifts the container and unloads the scrap into the furnace vessel. A basic oxygen furnace, or KOBM, is an enormous vessel that melts scrap and liquid iron together to create molten steel. After the scrap is loaded into the furnace, another crane loads the molten iron. Then, the furnace returns to an upright position and pure oxygen is injected from the top and bottom to melt and refine the mixture inside. After approximately 25 minutes, the initial operation is finished, and the steel then empties into a transfer ladle, which takes the steel to a ladle metallurgy facility. Here, steel samples are taken to determine if the properties are set to customer specifications. If necessary, alloys are added and mixed into the molten steel. If customers require ultra-low carbon steel, such as that used in the automotive industry, the liquid steel will move from ladle metallurgy to a vacuum degassing tank to have carbon levels reduced. Once the steel has been metallurgically refined, it moves on to a casting unit, where the steel empties from the ladle into a tun dish, which allows the molten steel to enter continuous molds. As the steel travels through the molds, water cools the steel to allow the advancing strands to solidify. As the strands progress onto run-out tables to form slabs, they are then torch cut to various lengths, depending on customer specifications. Other grades of steel can be made in an electric arc furnace, or EAF. While basic oxygen steelmaking combines 70% molten iron and 30% scrap, an EAF furnace can be charged with 100% scrap or 70% scrap and 30% molten iron. The contents are melted down by a combination of oxygen, natural gas, and electricity delivered through large carbon electrodes. The resulting liquid steel is poured from the EAF furnace into a transfer car, which moves on to ladle metallurgy and slab casting. Each slab is labeled with a code that will identify it through to its completion as a coil. Slab haulers transport slabs to storage areas where they remain until they are scheduled into the operation sequence at the hot mill. When it comes time for a slab to be rolled at the hot mill, it is routed to a reheat furnace, which heats the slab to its optimum rolling temperature of approximately 1200 degrees Celsius in about 2.5 hours. The heated slab travels to a roughing mill, where it passes back and forth between rolls to reduce the thickness in increments. To maintain surface quality, high-pressure water sprays remove any scale, which is the residue that can be left behind after reheating. As the strip enters the finishing mill, the lead end is cropped straight so that the strip will thread properly through the mill stands. The finishing mill reduces the thickness further according to the end-use requirements with a single pass. The steel strip passes through several stands, which contain rolls that apply pressure to the strip. Computer systems precisely control the roll gaps and speed, as each strip requires different amounts of pressure, and each mill stand turns faster than the one before. With the strip now at its required thickness, it passes through a cooling section, where banks of water sprays cool the top and bottom of the strip. Specific water flow rates and application patterns develop different metallurgical properties of the steel. The strip then enters the down coiler, where the lead end of the strip catches and wraps around a rotating mandrel that forms the strip into a coil. It's now ready to be transported to outside customers or to downstream finishing operations. The coil's tight formation prevents damage and collapse during storage and makes for easier transportation. Hot coils are moved from the hot mill to storage yards by 80-ton coil carriers. From here, coils are either shipped directly to customers who use hot-rolled steel, or they move on to pickling and cold rolling or tube making operations. These finishing operations further refine and condition the steel for customers who require value-added steel products. First, let's follow a coil on its journey through cold rolling. Coil transporters move coils from the storage yard to a coupled pickle line cold mill, or CPCM, for the first stage of the finishing process. A CPCM facility combines the cleaning and rolling processes of this initial stage in one continuous operation, which reduces maintenance and makes production more efficient. The cleaning stage is called pickling. During pickling, the coil is unwound and run through tanks filled with a hydrochloric acid solution, which removes the scale and oxides left during hot rolling or storage. If the customer requires it, the edge of the strip is trimmed immediately after pickling. At this point, the strip has a clean surface and the desired width for the next stage, cold rolling. The purpose of cold rolling is to refine the strip to the correct thickness, according to customer specifications. Similar to the process at the hot mill, the strip passes through a series of mill stands containing rolls that apply tension and pressure to refine the strip. As the strip exits cold rolling, it is recoiled and labeled for routing to other processes. At this stage, the steel must go through one more cleaning process to remove any residual oils before the next step, which involves heat. Oil residue could burn into the strip if it is not removed, so the steel is submerged into a heated caustic solution where the strip surface is cleaned, either by solution turbulence, roll brushes, or bubbles created by an electric current. Once clean, it moves on to an annealing furnace, which evenly heats the strip to create specific mechanical properties, according to customer requirements. There are 17 different annealing conditions to achieve diverse mechanical properties. There are 2 ways to anneal steel. With batch annealing, full coils are stacked onto a furnace base and then enclosed, while with tower annealing, coils are unwound and threaded through a succession of heating and cooling processes. After heating during annealing, the strip goes through the tempering process, which further refines the strip in 3 ways. First, the customer's desired surface finish is applied by textured rolls. The strip's shape and flatness is also further refined. In fact, the strip's thickness can be reduced by 20 to 30% beyond that achieved during cold rolling. Finally, tempering refines the strip's mechanical and metallurgical properties to the customer's desired levels. As you can see, it takes several operations to ensure the strip has the best forming and mechanical properties for the customer's requirements. But the process doesn't stop here. After tempering, cold rolled steel is either shipped to customers or sent on to a plating process. For example, galvanizing is a plating process that makes steel more corrosion resistant. To galvanize steel, cold rolled strip passes through a zinc bath, and as it emerges, a process called gas wiping maintains an even coating across the strip. From there, the coating dries. Some galvanized products require further tempering after coating to reduce thickness or to texture the surface for painting. Another plating process is tin plating, which prepares steel for use in packaging products for food, beverages, and paint. To create tin plate, cold roll strip enters electrolytic plating lines, or E-lines. In the E-lines, the strip passes through tanks of tin solution charged with an electric current. Following this coating process, the strip is given what's called a reflowing treatment, which gives the new tin plate its shiny finish. Finally, the strip is chemically treated to prepare the surface for customer use. Now that we've seen a hot-rolled coil's journey through cold rolling, let's take a step back and see it through tube making. Before a coil can turn from this into this, the strip must first be pickled, and then its width must be divided depending on the required tube diameter. This happens at the slitter, where the strip passes through blades and is rewound again in its divided sections. The slitter can produce coils that are 20, 24, or 30 inches wide. A crane loads the slitted coil onto the tube making line, where it is fed section by section into the strip accumulator. From there, it feeds into the welding section, where it is wrapped into a tube shape and then welded. A series of rolls further refines the tube's size and shape, after which it is cut into master lengths. These long sections of tube are cut down into smaller pieces so that they can be packaged. Tubes are then shipped to automotive customers, who use them to form vehicle parts through a process called hydroforming. Behind all of the sophisticated steel manufacturing processes is a league of people who maintain the elaborate system of machines and facilities that see steel through its journey. These people are responsible for making sure that the production systems deliver the best quality product while maintaining a safe workplace and minimizing impact to the environment. One group maintains the distribution systems and energy operations that power equipment. This includes electricity, natural gas, compressed air, hydrogen, nitrogen, city water, bay water, steam, and wind. Skilled tradespeople maintain all the equipment used to make steel. Some of the work is conducted in dedicated facilities for such work as vehicle maintenance, bearing and mill component repair, and machine maintenance. Other teams are mobile, working where maintenance and construction projects require services like masonry, welding, pipe fitting, scaffolding, mobile crane operation, and electrical repair. Making steel and steel products is an immense sequence of interconnected processes. Skillful teams of people maintain quality, accuracy, and precision at every stage so that customers receive the best products possible.